Welcome to Chemistry 112. We're going to do a quick review of Test 3. So you can use this to help you study. Go ahead and get started. Test 3. The first question asks, all the following substances may act as Lewis bases except. So we got to remember, Lewis acids, Lewis bases. How are they defined? A Lewis acid is defined as an electron pair acceptor, while a Lewis base is defined as a electron pair donor. OH minus still counts as electron pair donor. Everything that was an Arrhenius base and a Bronsted-Lowry base is still Lewis base. The only addition is there is an addition of certain bases that might not have been considered Lewis bases before. Now, ammonia, NH3, has a lone pair. Water, H2O, has 2 lone pairs. S2 minus has 4 lone pairs. The only molecule without lone pairs is BH3, which has below an octet and no lone pairs. BH3 would be a Lewis acid, but not a Lewis base. Question 2 involves salt. Salts. You got to think about how would you describe the pH of the following solution? We mix in zinc chloride. Would it be acidic, basic, neutral, or more information needed? So you need to split this into cation, anion pair and try to figure out if the cation would absorb base, the anion absorb acid, would both absorb acid and base, or would neither. So when you split this up to zinc 2 plus and chloride 1 minus. Chloride 1 minus, if it were to absorb acid, it would form HCl, which is a strong acid. Strong acids form salts, not weak bases. So Cl is neutral. Zinc, on the other hand, zinc 2 plus, can absorb base to form zinc hydroxide. It is a metal Lewis acid. So meaning when I put zinc chloride in solution, it would be an acidic solution. What is the concentration of Ba2 plus in a saturated barium carbonate solution? Looking at this, we need the KSP and an equation. So go into the doc cam. KSP for a BaCO3 reversibly goes to Ba2 plus and CO3 2 minus is going to be Ba2 plus times CO3 2 minus, which is going to be equal to x squared. So if I take my KSP and I square root it, I'm going to get the concentration of barium, the concentration of carbonate. So square root of 5.1 times 10 root negative 9 is 7.14, 10 to the negative 5th. Negative 5. Or answer D. Answer D. Question number 4. Acid rain has an average pH of 4.3. So what is the proton concentration? So the equation we need is pH equals negative log of H plus. Rearranging this to solve for H plus, we get 10 to the negative pH is equal to the concentration of H plus. So it's simply put 10 root negative 4.3 going to be 5.01 times 10 to the negative fifth. It'll be somewhere between 4 and 5. So 5.01. This one, determine the molarity of the acid in various Ka values. So you do have to read this chart to be able to pick out this number. So the numbers I'm going to write down: the concentration of base, 0.100 molar. The amount of acid, 25 mils. Uh, 25 mils. It's carbonic acid, diprotic. Now, the volume you need for the equivalence point is 25 and 50. 25 gets it to the first equivalence point. So in order to calculate the first equivalence point, you need MA, which we're calculating, VA, 25 mils, equals MB, 0.1, VB, 25 mils. It takes 50 mils to remove both protons, but it only takes 25 mils to remove one. Real quick, the molarity of acid would be 0.1 molar. Now, to define the pKa's, at half equivalence point, so half of 25, pH equals pKa. So 10 to the negative pH will give us our Kas. So I'm not going to come back to the .cam. I can do it from here. But at 12.5 mils, we'll say this is between, it's kind of hard to say, maybe like 1.5, I'll say 1.7. 1.7. So the pH at 10 to the negative 1.7 would be something like 1.99. So we'll say 2 times 10 to the negative second. Now at half, the second half equivalence point, which would be somewhere between halfway between 25 and 50, it would be 37.5. We'll say that's close to this line. We'll say it's close to this line here, which is between 6 and 7. Kind of hard to say. I mean, 6.2. We'll say 10 to the negative 10 root negative 6.2. So something like 6.31 times 10 to the negative 7th. The exact number is not as crucial as you trying to get close. What is the pH of a 0.5 molar solution of boric acid? pK of 5.89 times 10 to the negative 10th molar. Okay. Looking at this. With most acids, with the boric acid HBO3, so the BO3 where it splits into H plus and H2BO3 minus, you would have Ka equals x squared over our HA. So it's going to be a 5.89 E negative 10 equals x squared over 0.5. We solve for x, then we take the negative log of our x. So 5.89 times 10 root negative 10 times 0.5. We're going to square root that to get our x. X is equal to 1.72 times 10 to the negative fifth. Take the negative log of that. You get a pH of 4.76. 0.7, well, let's say 4.77. pH of 4.77. Answer is C. What is the pH of a 1 liter solution to which 25 grams of sodium hydroxide has been dissolved? This one's actually, it's easy but hard because you have to think about it. 25 grams in 1 liter, so 25 grams. The molar mass of sodium hydroxide is 40 grams in 1 mole and 1 liter. So what is the molarity of sodium hydroxide? The molarity is 0.625. Negative log of the molarity will give us POH. You have to remember that this is the POH. So negative log of 0.625 gives us 0.204. And so we'd say 14 minus 0.204 would give us 13.8. Is our pH 13.8. So that is how we had done the first 7 problems. Now keep moving. What is the pH of a solution of lactic acid and sodium lactate? So this is a buffer. The buffer. We have the Ka 4 times 10 to the negative 4th. You have HA is 0.75 and A minus is 0.4. Okay, looking at this. In this, we have a buffer equation is pH equals pKa log of A minus over HA. So our pKa is negative log of our Ka. 3.85. So we're adding log of 0.4 over 0.75. So you're adding to this a negative 0.27. 3.85 plus a negative 0.27 would give us 3.58. Or A. What is the pH of a solution containing 0.4 molar of acetate and sodium per hypochlorous acid and sodium chlorate? pKa, same problem. 10 to the negative 8th. We have HA is 0.4. A minus is 0.25. The only difference is that we're dealing with a much weaker acid. So in the case of this one, pKa is pKa is 7. So pKa is 7.53. Let's say 7.54. And our log of A minus over HA becomes negative 0.20. So you have 7.34 as our pH. 7.34 is our pH. 7.33 would work as well. Now, what is the pH of a 0.075 molar solution of nitric acid? Don't need to overthink this one. It is a strong acid, meaning just take the negative log of 0.075 would give us negative log 0.075. It's going to go to pH of 1.12. 1.12. Now, what concentration of fluoride would be dissolved in the mixture of calcium fluoride, KSP of 3.9 times 10 to the negative 11th? In this case, this one's a little bit trickier than last one because it splits into 1 calcium and 2 fluorides. So when we're looking at a KSP expression, it's KSP Ca2 plus and F minus squared, and F minus is 2x. So what we have, KSP is equal to 4x cubed. 4x cubed. Remembering that our concentration of fluoride is 2x. This is x and this is 2x. So we take 3.9 times 10 root negative 11th divided by 4, and then take the cube root. So 3 root answer. So you get x. X is equal to 2.14 times 10 to the negative 4th. But our answer is not this. Our answer is double that. So 2x is equal to 4.28, 10 to the negative 4th. So our correct answer for that one is, we'll just say B. Rounding up, 4.28 rounds up to 4.3. Okay. Keep going, keep going. What is the H plus present when we have 8.9 times 10 to the negative second molar NaOH? Don't overlook this one. It's rather easy. H plus times OH minus equals 10 to the negative 14th. Well, if we're given the OH minus, we can thusly know the H plus. So we're going to just say 10 to the negative 14th divided by our 8.9 e negative 2. Negative 14 by 8.9. You'd get the concentration is 1.12 10 to the negative 13th. So So D. Okay, 13 and 14 are the two titration problems. 25 mils of acid, 0.35 molar acid is titrated with 15 mils of the base of 0.15 molar base. What is the pH after this addition? So, pH after this initial addition. So not what is the initial pH, but what is the pH after? So we have to set up our ice table. Not so easy. We have to say, so here's our acid, here's our base, ICE. 25 times 0.35 equals 8.75. 15 times 0.15 is 2.25. So we're going to subtract out our 2.25 from both sides. How much base is left? 0. How much acid is left? 6.5 millimoles. Step 2, we have to turn 6.5 millimoles back into molarity. 25 plus 15, that's going to be 40 mils. So 6.5 divided by 40 is the molarity of acid is going to be 0.1625 m of acid. Negative log of this number, 1625. 1625 gives us 0.789. That's our pH. That's our pH. Continuing down. What would be the pH of 60 mils of base? Up to 60 mils of base. So we've changed it. So set up a new ice table. ICE. The acid is still the same. The base is changed. So 8.75. New one is 60 times 0.15. It'd be give us 9. So now we have more base than acid. 0 acid, 0.25 millimoles of base. 8.25 millimoles divided by our 25 plus 60, 8 divided by our 85. The molarity of base is 0.00294. Negative log of that will give us a POH, 294. We get 2.53 is our POH. And so 14 minus 2.53 gives us like 11.47. 11.47 is our pH after that. Okay. Last titration problem. Last titration problem. We're titrating a weak acid with 0.75. So in this case, we're given 0.75 molar base, 25 mils of the acid, and looking at the equivalence point, took 20 mils of the base. Now looking at the half equivalence point at pH 10, that is about, say, 4.1. So doing this, answering the molarity and the Ka again. Molarity and the Ka. Molarity, 0.75 times 20 equals 25 times molarity of acid. This time it's not so easy. We actually have to calculate this. The molarity of the base would be 0.6 molar. The Ka would be 10 to the negative 4.1. And that would be like something like 7.9 times 10 to the negative fifth. Okay. Okay. Almost done. Last 4 problems. pH of a 0.75 molar solution of rocket fuel, Kb of 1.7. So this is a base. This is a base, and I'm asking for what is the pH? 10 to the negative 6th. So it's going to be Kb equals x squared over base. And that's going to give us OH minus. We give us OH minus. So 1.7 times 10 to the negative 6th times our 0.75, and we're going to square root that, and that's going to give us our concentration of OH minus. 0.7 times 10 root negative 6. Shoot. 10 root negative 6 times 0.75. Concentration of base is actually 1.1. Let's say 3 times 10 to the negative third. Negative log of that. Negative log of 1.13 10 negative 3 is going to be 2.94. So 14 minus 2.94 gives us 11.06. 11.06. Or 11.05 in this case. Now, what acid-base pair could be used to achieve a buffer with pH 4? Now, here's the thing you actually got to check. Take the negative log of your Ka, and you want a pH that equals plus or minus 1 of 4. So Ka, note the Ka, negative log of C, which is a Ka, 5.9 times 10 to the negative second is 1.2. Is that plus or minus 4? No. What about D? Negative log of 9.5 times 10 root negative 8. That's 7. That's not plus or minus 1 of 4. Here's what tripped up most people. A and B are KBs. So if you took the negative log of 1.8 times 10 root negative 5, uh, 10 root negative 5, you would get 4.7. You say, oh, that's perfect, but that is a POH. So that one is bad. That is bad. You do that one more time. Negative log. So that would actually be a pH of what, like 9 something? 9.26. So last one, 4.3 times 10 root negative 10. 9.36. Subtract that from 14, you get 4.63. That's within plus or minus 1 pH unit of our buffer. So the correct answer is B. That was a tricky one. I highlighted them, I bolded them for you, but some people just looked right past it. 18, 19, and 20 are all thought questions. 18. What is the pH of a solution of ammonium cyanide? Ammonium cyanide. Well, ammonia is a Weak acid. Ammonium is a weak acid because it comes from ammonium hydroxide, a weak base. Cyanide is a weak base coming from hydrocyanic acid. So in this case, more information is needed. We don't know if this is more acidic or more basic without knowing the Kas and Kbs. That one, more information is needed. Which compound is more acidic? So this one's hard. Well, not really if you understand what I'm asking for, but if you don't know, this is kind of a guess. To be acidic, the more acidic compounds have more resonance structures and more electron withdrawing capabilities. So if I compared ethanol and trifluoroethanol, you would say B is more acidic than A. However, acetic acid, for example, C is more acidic than A because of the resonance. This is the ability to lose this. You can resonate that negative charge between the two oxygens. This is an acid. If I combine B with C together to get D, D is far more acidic than any of those because not only can it lose the acid and resonate, but then we can pull the electron density away with the trifluoro group. So D is the most acidic compound. Question 20. What is the pH of a 1 molar solution of sodium chloride? Well, sodium comes from sodium hydroxide, a strong base. Chloride comes from hydrochloric acid, a strong acid. Sodium chloride is just going to be a salt. We would expect it to be neutral. You may not find that to be such the case in lab, but we should expect it to be neutral. The last question, thinking of acids and bases, equilibrium and Le Chatelier's principle. Why is CO2 26 times more soluble than oxygen and water? Well, that has to do with a common acid, carbonic acid. When CO2 dissolves in water, it then can produce carbonic acid, which can then deprotonate itself in water. As it's shifting to carbonic acid and hydrogen carbonate, it is removing product from the last step. As it removes product from the last step, the reaction shifts to replace the product, and thus more CO2 is allowed to dissolve. Oxygen, which doesn't react with the water, it only has one equilibrium expression and thus is not going to benefit from this reaction. And so it's not going to get 26 times more soluble. Okay, that was the test. Thank you for your time. Hopefully this has been informative. Good luck on test 4.